Today we're going to discuss the sum and difference formulas. And so at this point, we know how to evaluate trig functions at angles that are pretty much multiples of pi over 2, pi over 3, pi over 4, and pi over 6. And what we want to do is we want to develop methods that will allow us to evaluate trig functions at other angles. And so the sum and difference formulas will allow us to do that. Now, normally I'll go through and I will derive these formulas, but I'm just going to list these formulas and I want you guys to be able to use the formula in order to help you evaluate trig functions. And I'll show you some of the times where you want to use these formulas, and so you'll know what to look out for. And so it says the sum and difference formulas are useful in situations where trig functions may involve a sum or a difference, or to help simplify trig functions at other angles that are not on the unit circle. And so we're going to start with our cosine, sum, and difference formulas. Of course, if it's a sum, it's going to be an addition of two angles. And if it's the difference formula, it's going to be a subtraction of two angles. And the formula for the cosine sum is given by, let's get our actual pen, cosine of that first angle, which is alpha, times the cosine of that second angle, beta, minus sine of alpha times the sine of beta. So notice here we have cosine of both angles multiplied together minus the sine evaluated at both angles and multiplied together. And there's a subtraction symbol there. The difference formula is going to look very similar, but the only difference is that the difference formula is going to have a plus sign in between. And so what this will do is help us to find the exact value of an expression that looks like this, the cosine of 5 pi over 12. Now, this is a hint to you guys, if you have an angle with a denominator of 12, then this is a hint that you're going to use a sum or difference formula in order to find the exact value. Now, I said that our trig functions are usually multiples of pi over 2, pi over 3, which is your 60 degrees, pi over 4, your 45 degrees, and pi over 6, which is your 30-degree angles, right? If I want to apply this formula, I want to use some of these angles. Now, I can use angles like 5 pi over 6 or 3 pi over 4 or 2 pi over 3 in the second quadrant, but 5 pi over 12 is not even pi over 2, so I'm going to focus on the angles in the first quadrant. Do know that you can use any angle in your unit circle when you're applying these formulas. But what I'm going to do here is I'm going to write these with the denominator of 12. That means I have to multiply the numerator and the denominator of this one by 6. And so I get 6 pi over 12. Multiply the numerator and denominator of this one by 4. So that's 4 pi over 12. This one would be 3 pi over 12. And this one right here would be 2 pi over 12. And so what I want to do is I know how to evaluate the sine and cosine at these angles. So if I could write 5 pi over 12 as the sum or difference of two of these angles, then I can apply this formula and it'll allow me to evaluate this trig function. And so what I'm going to do here is I'm going to write cosine of 5 pi over 12 as the cosine of 3 pi over 12 plus 2 pi over 12. Now, I chose those two because 3 pi over 12 is pi over 4. I know how to take the cosine and sine of. And then 2 pi over 12 is pi over 6, which I know how to evaluate my sine and my cosine at, right? So really, this is, I'm going to write them in their simplified form. That'll be a pi over 4 plus a pi over 6. And now I can apply this formula, right? And so this is a plus sign. I'm going to use this formula here. And so this will equal the cosine of pi over 4 times the cosine of pi over 6 minus the sine of pi over 4 times the sine of pi over 6. And now, again, I chose these angles specifically because now I can evaluate my trig function here. This is a 4 here. It looks like a 9. That's a 4. But the cosine of pi over 4 is square root of 2 over 2. The cosine of pi over 6 is the square root of 3 over 2. Sine of pi over 4, square root of 2 over 2. Sine of pi over 6 is 1/2, right? So I have those products that I'm going to subtract from each other. So this is going to be the square root of 6 over 4 minus the square root of 2 over 4. And this is what this trig function equals. So this is the exact value. All right, let's go to part B here. I have the cosine of pi over 6 times the cosine of pi over 3 minus the sine of pi over 6 times the sine of pi over 3. Now, note here, we do not have to use any formulas here because we know how to take the cosine of pi over 6. We know how to take the cosine of pi over 3. Same thing with the sine. However, I'm going to shorten this up a little bit. Instead of evaluating at all of those different functions, I'm going to look at this and I can tell right now that this really fits the right-hand side of this formula that we just got finished using, the cosine of alpha plus beta. And so what I'm going to do here is I'm going to write that as a cosine of pi over 6 plus pi over 3. Now, pi over 6 plus pi over 3, well, this is 2 pi over 6, and if I add that 1 pi over 6, I get 3 pi over 6, or pi over 2. And when I simplify that, the cosine of pi over 2 is 0. Now, let's just check that to see if that's what we get if we evaluated this, right? Remember, the cosine of pi over 6 is square root of 3 over 2. The cosine of pi over 3 is 1/2. All right, the sine of pi over 6 is 1/2. The sine of pi over 3 is square root of 3 over 2, right? Notice these two are the exact same expressions, and so we end up getting 0. Now, you might find that this was quicker, but I just wanted you to be able to recognize that this is actually the sum formula written out in its full expanded form. And so we can write it in a simple form by doing the cosine of pi over 2 and just evaluate one single trig function. And so either way we do it, we're going to get the answer of 0. Let's get to the sine sum and difference formulas. All right, my sine sum and difference formula, if it's sine of alpha plus beta is going to be the sine of alpha times the cosine of beta plus cosine alpha sine of beta. See, even I get these formulas confused. It's just a bunch of formulas. All right, so this plus sign is going to stay a plus sign, and you basically do the difference. You do sine, cosine, and then cosine sine of the first angle and the second angle. And so the subtraction is going to be sine alpha cosine beta as well, but now we're going to have the minus cosine alpha sine beta. All right, and then I'm going to go ahead and give you the tangent sum and difference formulas. Tangent alpha plus tangent of beta equals the tangent of alpha plus tangent of beta divided by 1 minus the tangent of alpha tangent of beta. And you can get this formula by basically doing the sine of alpha plus beta over the cosine of alpha plus beta and then simplifying, all right? And again, I'm not going to derive that. The difference between the sum and the difference is that the difference is going to have tangent of alpha minus tangent of beta in our numerator. And then we have 1 plus tangent alpha, tangent beta. All right. I will tell you that you do not have to memorize these formulas. I will give you these formulas, but although I say that, it's your best bet to memorize them so that you can get used to using them. All right. So that you can get used to using them. All right. Let's look at some examples. All right. I have the sine of pi over 12. Again, remember, we said that pi over 2 was 6 pi over 12. Pi over 3 was 4 pi over 12. Pi over 4 was 3 pi over 12. And pi over 6 was 2. That's a comma. 2 pi over 12. I probably didn't do it in that order before. And so if I want to find the sine of pi over 12, then what I could do is I could rewrite this as the sine of, okay, I can choose multiple ways to do here. I can do the 4 pi over 12 minus 3 pi over 12, or I can do the 3 pi over 12 minus 2 pi over 12. I'm going to choose the smaller numbers. And the reason why I'm writing it this way is because I know these angles here. 3 pi over 12 is pi over 4. 2 pi over 12 is pi over 6. And now that I know my two angles that I'm subtracting, then all I have to do is go to my difference formula, which is sitting here, and put that first angle where I see the alphas and put that second angle where I see the betas. And so this is going to equal sine alpha, or pi over 4, cosine pi over 6, minus cosine pi over 4, sine pi over 6. And then now we can evaluate our trig functions. Square root of 2 over 2 times square root of 3 over 2 minus square root of 2 over 2 times 1/2. And so we get square root of 6 over 4 minus square root of 2 over 4. And that is what our trig function equals here. That's the sine of pi over 12. Notice here, this denominator was a 12. All right. In the last example, the denominator was a 12. And so usually if you can write if your denominator of your trig function is written in radians, so you have pi on the top and 12 in the denominator, your best bet is to use one of your sum or difference formulas. Let's go to this example here, tangent of negative 15 degrees, right? Well, for one, I could write this as the tangent of 30 degrees minus 45 degrees, right? That'll give me a negative 15. And then now I know my two functions here, and I can apply my tangent difference formula, my different formula for my tangent function here, which is that formula there. And so I'm going to put 30 degrees in for alpha, 45 degrees in for beta, and I'm going to get tangent of 30 degrees minus the tangent of 45 degrees all over 1 plus the tangent of 30 degrees times the tangent of 45 degrees, right? And so this is my function, or my expression. Now let's simplify it. Well, the tangent of 30 degrees, remember your 30-degree angle is, the y-coordinate is 1/2, the x-coordinate is square root of 3 over 2. And so when you do that division, you're going to get square root of 3 over 3. The tangent of 45 degrees is 1. And so in our denominator, we're going to get square root of 3 over 3 times 1. And so this basically simplifies to this thing here. Now, this is not very simplified, right? This is a complex fraction, and so one of the things we want to do is we want to multiply the numerator and the denominator by the LCD. The LCD of all of those fractions within that complex fraction is 3. Notice we have to distribute this 3 here and to here, and we're going to distribute this 3 to here and here. When you distribute it to the fraction, you're going to get, the 3's are going to cancel, and so you're going to get just the square root of 3. 1 times 3 is 3. All right, now what we want to do is we always want to rationalize our denominator. When your denominator has 2 terms, you multiply the numerator and denominator by the conjugate of the fraction in the denominator. The fraction in the denominator is, radical expression in the denominator. Its conjugate is the same thing, but separated by the opposite sign. And so since that's a plus square root of 3 there, I'm going to multiply the top and the bottom by 3 minus the square root of 3. In my numerator, when I FOIL everything out, right, I'm going to get 3 square root of 3. I'm going to go this way this time. Minus 3 minus 9 plus 3 square root of 3. And that denominator is a difference of squares. So if I take the first thing squared, I'm going to get 9. And the second thing squared, I get 3. And so this simplifies. Well, this 3 square root of 3 and that 3 square root of 3, they add together to 6 square root of 3. And negative 3 minus 9 is negative 12. And that denominator has a 6. Well, if I divide both of those denominators by 6, we're going to get square root of 3 minus 2. And so that tangent of negative 15 degrees is the same thing as square root of 3 minus 2. And this is the most simplified, and this is the way we want to go, right? We want to get rid of the radicals that are in the denominator, and this process will help us get there. And so probably using the formula is the easy part, right? Because you're going to be given that formula. The simplifying is a lot of steps here. And so you got to get used to that. All right, we're going to look at 2 more examples because another relationship between our functions, our trig functions, is going to come from this. Notice here I have a pi over 2 minus x. Notice it's a pi over 2 first and a minus x second, all right? What I want to do is I'm going to simplify this. Well, I have a subtraction, so I can use the difference formula for my cosine function. So that would be a cosine of pi over 2 cosine of x plus the sine of pi over 2 times the sine of x. Well, the cosine of pi over 2 is 0, so that's 0 times cosine of x. The sine of pi over 2 is 1, and that would be 1 times the sine of x. Well, 0 times anything is 0, 1 times anything is that anything, and I get the sine of x. And so when I do the cosine of pi over 2 minus x, this is the sine of x. All right, look at that. I'm going to do the same thing or a similar thing here for our sine function. Now I'm going to use my sine difference formula. I'm going to have the sine of pi over 2 times the cosine of x minus the cosine of pi over 2 times the sine of x. Sine of x is 1. Sine of pi over 2 is 1, so I get 1 times the cosine of x. Cosine of pi over 2 is 0 times the sine of x. 0 times anything is 0. 1 times anything is that anything. And I'm going to get cosine of x. So when I did the sine of pi over 2 minus x, I got the cosine of x. And when I did the cosine of pi over 2 minus x, I got sine of x. All right, this relationship is always going to happen for this form right here. The input into this cosine function and this sine function in the initial problem that I gave you were pi over 2 minus x. Remember, your pi over 2 is like a 90-degree angle. That's 90 degrees. That's 90 degrees. The angles x and pi over 2 minus x, these two angles, they differ by 90 degrees. If I add these two angles together, so if I take the input here and this input here, I get x plus pi over 2 minus x. When I add those two together, I get pi over 2, which is 90 degrees. So when two angles add up to 90 degrees, we call those complementary angles. So, okay, I don't know if this is the right way to spell complementary, if that's supposed to be an I there, but they're complementary angles, I forgot. Okay. Vocabulary, spelling is not my strong suit here, right? But I'm quite sure that's it. And if I'm wrong, I'm sorry. But complementary, right? Complements are right. And so you can spell it like the word complement. All right. And so these two angles are complementary. Angles that add up to 90 degrees, a pair of angles that add up to 90 degrees are called complementary angles. And so if the cosine of some angle is going to always equal to the sine of its complement, all right? And then the sine of an angle is always going to equal the cosine of its complementary angle, or its complement. The angle that makes a complementary angle with it is called the complement. Notice sine and cosine have the same root word, which is sine, but cosine has the prefix co. Sine and cosine are called cofunctions. And so this relationship that when we evaluate at an angle we find the trig function at an angle, it's always going to equal the cofunction evaluated at the complement of that angle. All right. So the cosine of some angle is going to equal the sine of the complementary angle, and the sine of some angle is going to be equal to the cosine of its complement. All right. This not only happens with sine and cosine, it happens with secant and cosecant, and it also happens with tangent and cotangent. This is going to be called what we call the cofunctions, cofunction identities. The value of any trig function at x is equal to the value of its complement, our cofunction, at pi over 2 minus x, and that's the complement there. All right. So the cosine of pi over 2 minus x is the cofunction sine of x. The sine of pi over 2 minus x is the cofunction, which is cosine of x. And I was about to type in the whole word, but we want the abbreviation since we're using function notation. Same thing happens for secant and cosecant. And so the secant at this angle is going to equal the cosecant at its complement, which is x. The cosecant at this angle is going to be equal to the secant at its complement, which is x. And the same thing happens for tangent and cotangent. And so this will be cotangent of x, and this will be tangent of x. And so last but not least in this video, we're going to verify this identity. All right, verifying an identity is basically working on one side of the identity until you get to the other side. All right, and so what I'm going to do is I'm going to start on this left-hand side here, and I'm going to try to rewrite this expression over here. That's what we mean by verify the identity. All right, and so what this is this looks like the cofunction identity. The difference is that it has x minus pi over 2, whereas these cofunction identities have pi over 2 minus x. What I'm going to do is I'm going to write on one side, and I'm going to keep bringing my equal sign down. I'm going to rewrite this. I'm going to factor out a -1. When I factor out a -1, I'm going to get a negative x plus pi over 2, right? And the reason why I'm doing this is because if I do that, I can write that as pi over 2 minus x. So that allows me to switch the order. And notice here, this is a negative sign of this angle here. Well, my cosine function is an even function. So remember when we talked about even functions, f of negative x is the same thing as f of positive x, right? And so this -1 doesn't matter. So this is exactly the same as doing the cosine of pi over 2 minus x. All right. And now I know that this thing equals the sine of x because that's a cofunction. The cofunction to cosine is sine, and this will be a complementary angle. This will make a complementary angle with the angle pi over 2 minus x. And so now I have this. Now I see the x completely by itself. That's good because this side of my equation or my identity here has only x's. What I'm going to do in order to see this side is I got to start seeing some cosines, right? So I'm going to multiply by cosine of x over cosine of x. Now, I know that sounds like it's completely out of the blue, but I'm using some strategy here because I need a product of two things, and so I can always multiply by 1 by doing a fraction, right? Ensuring that the numerator and the denominator are the same. And so when I write it this way, notice here, now this is over 1, right? All I have to do is multiply across the top and multiply across the bottom. Well, when you multiply, the order really doesn't matter, right? And so this would be, I can write that as sine of x over cosine of x. The order doesn't matter when I multiply, so I just switch the denominators. It's going to be the same thing when I multiply anyway. And so I'm going to write this as a cosine of x, and I'm going to use my quotient identity that says that sine x over cosine x is tangent of x. Notice here, I worked with completely on one side of my equation here until I got to the bottom, and I ended up with the equation or the expression on the right side of my equation. This is the process. This process is called verifying an identity. All right. We sort of skipped over a whole section of verifying identities, which makes you good at these trigonometric identities so that you can get used to seeing and visualizing when to use identities. But I did want to show you an example of doing this. Notice here, we did some algebra in these steps here. Call it algebra or simplifying. Anytime I factor or do something like that, I'm going to call that algebra. And then at this step to this step, we use the cofunction identity. I'm going to abbreviate that with identity. And then I go from this step to this step. Oh, there's algebra. I'm just multiplying by a function over a function, right? This right here, this is also algebra. I'm changing the way that things look, right? The order doesn't matter when I multiply. And I can multiply this function first and this function second here. And then I use my quotient identity. All right. And this allowed me to go from this side of this equation to get to this side here. When you verify an identity, you don't do anything to the other side. You just basically prove that this left-hand side equals that right-hand side. All right, that's it for this video. I'll see you during the next video.